Okay, so today we are going to move to a whole new word, sound, in which we'll stay next week also. I don't know until the end, depends how it will go. But first, I want to... Why is it not working? I want to clarify something that Harry asked me last time. I showed you this graph that we see every time we buy a light bulb. It appears there and it shows the color temperature. And Harry asked me about the coordinates and what does this graph means, and I didn't know how to answer, so I checked. So, and it's relevant for everybody. So we said that our perceptual organization of colors is different from how wave-like, which is a linear, a linear gradual. So this picture is what the International Commission of Illumination, which is la Commission Internationale d'Éclairage in 1931, so they build this is a color, it's a Cartesian organization of our the way we perceive color. So what it means is that if you take this here, this line, the outer lines from here to here, is the pure colors, the wavelength of the pure colors. And if we, let's see if I can annotate, it works? Yes. So let's say if you add this light and this light, why it's not working? So this light and this light in the same intensity, our perception will be exactly here. If you add this light with the double intensity together with this light, so we will perceive this color here. If you add a third light from here, then this one, so we will perceive the epicenter of this tree somewhere around here. Okay, so this is used whenever for color management, whenever you want, let's say, you want on a screen, on a monitor, you want the viewer to perceive this color, you can know exactly which combination and which intensity of which lights are emitted in order to achieve it. Okay? So here in this slide, there is an explanation of some other stuff. How can I unannotate? Clear all drawings. All right. Later you can check. It will be on the slides. So what I showed you here is like when you, for a black body radiator, these are the temperatures in Kelvin, which is absolute temperature, and that's the colors they emit for each temperature. All right. All right. So let's move to, why is it here? To sound. So usually discourse, perception, traditionally it focuses exclusively on the senses of vision and hearing. First, because most of the research in perception has been on these two modalities, and we feel that maybe we understand them better. I don't know if that's right. And also it's a choice that it's maybe preferable to go deeper into these two modalities and leave aside touch, smell, and taste. Intuitively, we feel that vision and hearing are the most important ones. Again, that's very subjective. So vision, it's something in itself because the stimulus is electromagnetic light energy. And hearing is mechanical stimulus that we will understand today. And actually, the hearing apparatus, the mechanical things we have inside, it's very complex and interesting. It's very ingenious, whoever invented it. So today we are going to talk only about sound. And then we'll move to anatomy next week. So as you already understood, we need to learn both the physical properties of the stimulus and also the anatomy, because our perceptual interpretation for any modality is a function of, and therefore is limited by, the interactions between the physical stimuli and the physiological mechanisms that we have. And we already understood that the main thing is limited by this interaction. So our sensations for any modality is a translation from stimuli, the outside world, through our receptors that transform whatever energy reached them into electrical activity that is transmitted along our perceptual neural pathways. And next week we'll see that hair cells are the specific mechanism, the specific, it would be like the cones and the rods, that they translate mechanical energy into electrical energy. So if you it works especially if you have a subwoofer that transmit the bass, the low frequency sound waves. It actually, the membrane of the speaker, it moves, and it moves in a certain frequency, and that's what, and this vibration, it moves the medium around us, be that air or water, whatever, wherever our head is inside, it moves the medium, and whenever this vibration reaches our eardrum, our receptive mechanism, it's translated into electricity. So just like, so we have air molecules, and imagine a coil. If you push a coil, it will compress and depress in a kind of a wave. Imagine a slicky that children, I don't know, it was in the 80s mainly. So because the amount of molecules at a given space remains the same, so when something pushes, let's say this is the membrane of a speaker, whenever it pushes it, so first it compresses, and then the wave continues, like in a pond, like when a stone falls in a pond, and so you have a wave of compressed molecules followed by sparse density, followed by, again, imagine a room full of people, nobody's moving. If someone pushes someone, so first there will be more space between the two, and then the pushed person will push other people, and after it pushes the other people, it will the person will come back, and you have a wave. So the way it propagates depends on the density, how many people there are in the room. So for any given space, there is a static resting density, which is a function of the space and the amount of things in that space. So for air, because of gravity, the closer we are to the Earth's surface, there are more molecules per square meter. So they are more densely packed. So all we'll talk about today, all the references and the numbers, they relate to the density of air on the surface. Okay. Which means that so underwater we hear just as well, even better for some frequencies, because water is denser. Actually, we hear the speed of sound on the surface of the Earth is something about 340 meters per second. Underwater, it's five times faster. It's something like 1,500 meters per second. Which also means that in the vacuum, we don't hear sounds. We cannot hear sounds because there is no medium, theoretically, that propagates movement. So just like with light, our system reacts the mechanical system that we'll see next time, it reacts only to a very specific short range of vibration. Even though any movement results in vibrations, in air waves. Okay. So sound is a perceptual phenomenon, not a physical one. The physical phenomenon is differences, wave in air pressure that propagates through air or whatever we are. So whenever there is a vibration, whenever a wave of sound, well, sound pressure, we use this word, but this is not accurate because sound, as I just said, is a perceived sensation. What propagates is air pressure. So these waves, the pattern of these waves, the frequency, which is, let's say here in this picture, the distance between the sparse density and the condensation, this remains the same a long distance. These fluctuations, they don't change along the propagation. What changes is the amplitude, the strength of those waves. So the further the source of the movement, of the vibration, the less the amplitude, the strength, it dissipates. I'll explain it soon. The physical strength of the sound wave, it decreases. So this is, if you can see, this is along space. So the pattern remains the same, but it goes and decreases. So energy is conserved, as we know, or theoretically conserved. So imagine that when a stone falls on a pond, the energy released is the wave in this area. So with time, these waves continue to propagate, but it spread along a larger area larger and larger area. Depends on the medium, depends on the vibration. So the larger the area, the same amount of energy that is conserved is spread along that area. So the frequency of those waves, the pattern of the waves remain the same, but the height of the waves, they go and decrease. So the equation of area is of a sphere, because air, when something moves, it's a sphere, right? It's 4 pi, the radius of the area, squared. So if you double the distance of the area, you have 4 times more area. If you double the radius, the distance from the source, you have 4 times more area propagated. So if you triple the distance, it will be 9 times more area. So the energy dissipates according to the area. Theoretically, there is also friction and inertia, but we can consider that the energy is conserved. All right, so here we see distance, and it dissipates by this proportion, more or less. Okay, so sound waves or air pressure waves, they work like this, not like we have seen with light electromagnetic waves. So as I said before, it's like a coil. Imagine that these are the molecules of air. They remain in the same location, more or less, but they are compressed and then sparsed and compressed and sparsed. And this energy is what propagates. So this is only a depiction. This is not a picture of the wave. This is only a depiction of the air pressure along time. So we can represent sound waves, and again, I'm saying sound waves, it's air pressure waves, but that's the way we, even though it's not accurate, that's the way we usually refer to it. So we can represent by a given location over time. So this is one cycle. So this is a given period of time, or we can represent it along for a given time along space, depending on what we are trying to understand. One or the other is more useful. So the amplitude, meaning the strength of a wave, is the difference, the distance from its resting state. So imagine that our eardrum is like a stretched membrane. So when movement, when vibration reaches it, it will deflect to both sides from its resting state. So the amplitude of a sound wave is the difference from its resting state. It's not the entire distance from its lower, the depressed to the other side. Okay. So here we are depicting for a sound wave one cycle for a given in one location. So this is time. We have a given time here. So the way the units of sound waves is we use hertz. Hertz is cycles per second. It can be anything. Whatever is has a wave form. So we take one cycle and divide by second. So when we have a sound wave of 250 hertz, it means that these going up and down back to the same place occurs 250 times per second. All right? And this is the frequency. The frequency is what determines the pitch. So pitch is the perceptual translation of frequency inside our system. And just like colors are a related, it's not a perfectly correlated translation. So we can have different electromagnetic waves that we perceive as one color, and different combinations can we perceive as the same color. So the same for frequency and pitch. It's only related, it's not exactly the same. We'll see it soon. And loudness is our perceived sensation for the amplitude, for the strength of the light wave. Okay? So now let's hear some pure tones. Pure tones are something that rarely occur in the world, and they are pretty annoying. So put your hand in be prepared to adjust your sound if it's too loud. So first, 250 hertz sounds like this. Okay, now 1000 hertz. And now 4000 hertz. So these are pure sounds, pure tones. When for the musicians among you, when how do you call it? The anyone? The pitchfork? Yes. The when you give a gleam to the pitchfork, it emits a closer to a pure tone. So again, the physical stimuli are frequency and amplitude. We can measure directly. Loudness and pitch we can only indirectly measure by observing perceptual reactions of people. So here what we have is the sound wave of 1000 hertz for 1 millisecond, because if it's 1000 times in a second, and this is one cycle, so we have 1 second divided by 1000, it's 1 millisecond. So this is the same sound wave, the same frequency, but with a much larger amplitude than this. It's 3 times, I don't know, something like that, the amplitude. It will sound the same, but much, much louder. So the same for 10,000 hertz. So here we have 10 cycles within 1 millisecond. And the same perceived sound, but much louder. And I will not torture you with this. So let me give you 1 minute to answer this. I'm completely dark. I have been dark all the time. All right. So this one has a lower frequency and a higher amplitude, that's sound 2. so it was an easy one. Almost everybody got it right. Let me close it. Where were we? We are here. Okay. This is students, usually not only students, people don't like decibels because it's logarithm, but it's not that complicated. Let's try. That's how we measure sound, the pressure levels. So first, let me remind you what are logarithms. So a logarithm is a transformation from a geometric progression into an arithmetic one. So the question is, to which power the base that here is 2, to which power it must be raised in order to reach 512. So it's 2 raised to 9, right? So it's 9 times 2 times 2 times 2 times 2 times 2 will be 512. So this is logarithms. So why do we use it? So I'll give you an example. Let's say that a biologist wants to count the number of generations that an egg divides. So every time an egg, a fertilized egg, divides, it divides itself in 2, a long time. So a biologist wants to count how many divisions it happens per day. So if you count the number of cells you have each day, it's uncomfortable. You cannot visualize it well. So what you do, you calculate the logarithm in the base of 2. If the cell would divide itself every time into 3, the base would be 3. Okay? And then you have the number of generations per day. Okay? And that's much more comfortable for us to visualize. So sound pressure, we have this same problem. The difference between what we perceive as a much louder sound, it multiplies itself by, you'll see soon, by very large numbers. So most of the sounds that we perceive in our day-to-day, in order for us to depict everything in one graph, they would be all squeezed in the beginning here. A subway here in New York, which is extremely loud, look, where is it? And this is a takeoff. So what we do, so this would be a linear depiction. So if we move to a logarithm scale, it's much more manageable for us to perceive it, for us scientists. So let's understand what is it exactly. So first of all, forget about this line. This is what used to be. Everything, when we talk about decibels, it's according to this equation. So decibels, sound pressure levels, are 220 times the logarithm to the base of 10 of the minimum threshold, a given sound wave divided by the minimum threshold. So this reference is the minimum threshold. The 0 is the minimum threshold for a 3000 hertz sound, a pure tone. At Pascal is a unit of pressure. So for a given height from the surface of Earth. So what we have here, let's see. If you increase this number, so here we have the reference, if we increase it by 10, so to which power the base 10 must be raised in order to be 10 times the reference? 1, right? 10 raised to 1 would be 10 times 20. So the increase of 10 times a given sound would be the same as increasing 10 decibels. And we can see it here. This is the minimum threshold, 0 decibels. If you, I said 10 is 20. It's 20 times 1, right? So it's 20 decibels for 10 times increase. So if you increase 40 decibels, you are increasing 40 divided by 20 would be 2. So 2 here, times 2, it will be 100, right? So if you increase a given sound, its amplitude, its strength by 100 times, you are increasing 40 decibels. Is it clear? Can you see it? Yes, no. My room is too dark, it's not any. Anyone is not following it? All right, so I have a question for you. If you buy earplugs, which it's written on the box that they attenuate, they decrease the sound by 40 decibels. How much is it attenuating the sound waves, the physical stimulus? Anyone in the chat? By 100, yes, right? Okay, can you see it? From 0 to 40 is 100 times. Sounds that it's usually, if you open your iPhone now, there is this, you can, it explains inside the new system, you can stop when you hear through your earphones. It can, how do you say it? It can limit the amount of sound to a certain level, and it's usually 85 decibels. We'll understand soon. It's additive, it's per time, but usually sounds above 85 decibels, they start to damage the system. Okay, so the threshold for that our system, the minimum amount of sound for us to perceive sound, the minimum amount of amplitude depends on the frequency of the sound. So if, and I will not do it, if I play a 400 hertz sound that decreases, the amplitude decreases in time, it will sound like a ba, 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 and then you would count until you cannot hear it anymore, compared to 1,000 hertz, or 8,000 hertz that I cannot do. We would count more repetitions in the area of 1,000 hertz. We will stop hearing the same amplitude for 400 hertz and 8,000 hertz before we would stop perceiving sound for 1,000 hertz. And this is a complicated, we will spend some minutes talking about this here. What we have here, first of all, on the abscissa we have frequency. And usually, well, here it starts with, we hear from around 40 hertz. Dogs hear 20 hertz, maybe even less. We hear from 40 hertz, so this is 50. I don't think we hear these sounds here. But anyways, and we hear until 15,000 hertz, or left 12,000 hertz. So this is frequency, and the ordinate we have the logarithm scale of decibels, of sound pressure levels. So first of all, so this is, it's green, right? Is it green? So here we have the minimum threshold. What do we see? Someone wants to explain what does it mean that it's curved like this? Anyone wants to try? Can you hear sound B?
Yes.
Yes. Can you hear sound A?
No.
No. Even though they are the same intensity, they are both 40 decibels, right? But within this range, we can perceive it. Here we cannot. So obviously, as we can see, we are mostly sensitive to this range between 1,000 and 7,000 decibels, hertz. Now, how come we have minus decibels? Anyone? So we said before that the minimum threshold upon which 0 decibels is calculated is 3,000 hertz. And for, which is around here. So for 4,000 hertz, we have a lower threshold, more sensitivity. This is the area of normal human conversational speech, which is between 40 and 60 decibels, between 400, something like that, and almost 5,000. So this is the area of normal people talking. This is the sound waves. And it makes sense that we have more sensitivity to those here in this area. Equal loudness curves, meaning that, so anyone who can explain what is the difference between D and C? Anyone? Well, what can you say? What can you say from this graph between D and C? Equal loudness curves.
Even though the decibel is different, we feel equal loudness?
Yes, we perceive them. They have different pitches. They sound like different sounds. But if you ask a participant, the participant will perceive them as the same loudness. It's funny. It's like two different sounds. And if you, in an experiment, okay, compare this sound, this violin to this piano. Tell me when, and you present them at different decibels until the participant says, oh, this feels like equivalent loudness. And it makes sense because we are more sensitive to 1,000 hertz than to 100 hertz. And we can also see that the louder the sound, the more intense the more decibels, the sound pressure level, the flatter is the line. And this is the threshold of pain. So we said that above this area, we start to accumulate damage to our system. And here we literally feel pain. Okay. Now, a question. Your iPhone, it has, I don't know if you have to download an app, there are many like those, or if already comes, it can measure the decibels of a given ambience. So you open your iPhone in a room, and it tells you that the ambient sound is 60 decibels. How do you know how loud it will feel for someone? Can you know how loud it will feel for someone? Compared to another room where the iPhone measures 50 decibels. Let's say two rooms. One, you measure 50 decibels, the other 60 decibels. Can you know which one will feel louder? No, you cannot, because it depends on the frequencies of the sounds, right? We can see it here. So 50, I said 50 and 60, so 50 here can feel louder if it's here than 60 somewhere here or here, right? Now let's say that you are in a room with a sound around 300 hertz at 60 decibels, and another room that sounds with sounds around 6,000 hertz with 60 decibels. Which one will feel louder? You don't want to play with me today, right? The second, yes, right? So this is 60. This is 60. 300 will be here, and 6,000 would be here. So according to this function, we will hear the second one, 60 decibels at 6,000 hertz. We will feel it louder. Okay. Let's say we have the same frequency for a given frequency. If we increase the decibels, will it feel louder? Yes, always. It doesn't matter which frequency. If you increase the decibel, it will feel louder. Now let's say that you maintain the decibels, the amplitude, and you increase for one. Choose one of the decibels, one of these horizontal lines. You maintain the same decibel and you increase the frequency. Will it sound louder? Yes. Sure. Always. Maho? Not only you don't know, Maho, we don't know. We cannot know because it depends on which part, which frequency. So if you increase, if you are at 60 decibels for lower frequencies and you increase the frequency, it will sound louder. But if you are around here for higher frequencies and you increase the frequency, it will sound lower. Make sense? It was a trick question. Not that tricky, come on. But does it? Can you understand why we cannot? It depends on the frequency, because here it goes down and here it goes up. The threshold, the sensitivity. Okay? So for the same level, intensity of the sound, if you increase the frequency, if you go to the right, depends where you begin, it can sound louder until here, more or less, but it will sound lower from here on. Yes? We all agree? So I said that above 85 decibels, we start to have damage. So it's a cumulative thing. It's per week or months. If you hear for a very short period of time something extremely loud, even for, if it's extremely loud, even for seconds, you can already have damage in your system. But for something like, so we said that subway, when the trains, when the car, they stop, the brakes, they make this horrible squeaking sound, and they reach up to 120 decibels. So if you spend a lot of time in the subway, it will accumulate, and it will, you will have damage. So for all of you, me included, when we spend a lot of time in the subway, put earplugs or even good earphones. It helps. It makes a difference. When I was in the army, it was almost 30 years ago, 25, 30 years ago. So it was before nowadays they have rules. But we had trainings, some of our firing trainings, we would do it without earplugs, because the rationale, and it makes sense, it does make sense. The rationale was that we had to get used to the sound of firing without any protection, because in real time we wouldn't get started, we would be used to it. The problem is that it's really, really damaging. So soldiers from my generation and below, many have hearing problems from the army. Nowadays, in any situation, in training, they must wear earplugs. Once we were also taken, I don't know, it was like a fun day. It was, it was like they decided to take us in a fun day to Air Force base. And they took us to the landing field, to the thing, and we were like, I don't know, on the standing there. Sounds like it's so dangerous. We were like 30 soldiers standing on the border of that narrow strip, and F-16s were taking off. You cannot imagine the sound. We were all like this, but it was unbelievable. It really hurt. And I am sure that even once hearing that sound it damages your hearing. Hearing loss. So presbycusis means old people's hearing in Greek, just like presbyopia is old people's vision. So what we have here, this 0 means no loss, and this is age. This is frequency. So what we can see is that women, they start above 50 years old, 50 to 60 years old, they start to lose hearing, 10 decibels for all ranges. And for higher ranges, it gets worse. And with age, it gets much worse. And with men, it's even worse. We can see that men lose more, faster, and earlier. Now, I suppose, but I think it makes sense, that this is not an inherent difference between men and women, because this is an average for a given population. And it's probably because of there are much more men that work in noisy environments than women. And actually, it has been, I looked through, I didn't find it, I have time to, but it has, I remember that I saw somewhere or read somewhere that old people that live, like, I don't know, tribes that live in remote areas away from civilization where noise levels are usually lower, they lose hearing in a much less acute way with age. So it makes sense that it's the difference between the average of I don't know, professions or something like that. In my family, there was a funny story. My great-grandmother was very German and very Jewish, and she was already 90-something. She couldn't hear well anymore. And many times she would like ignore my mother. But she loved my father. So she would never ignore him. And every time he talked to her, she would talk to him. And with my mother, she would do as if she couldn't hear. So the gossip in the family is that she was like, making, German Jewish manipulations with my mother, but actually it makes sense because my father has a very deep voice, and my mother, she has a normal feminine voice, so maybe she really didn't hear my mother. So theoretically, for old people, I don't know if it's true. I'm just by logic. Theoretically, for old people that don't hear well, if you talk to them like with a lower voice, they'll probably hear better. All right, the Fourier representation of sound, which is, Fourier was a mathematician, Joseph Fourier. I think he was also, I'm not sure if he was also something else. So Fourier series is used, those of you that know mathematics, it's a very useful way to represent and calculate a lot of stuff. So for sound also, we have the Fourier representation here on the bottom. This is the Fourier representation. And it's practical to represent complex waves, when waves are the summarization of waves. So here what we have, so tell me something, how long is this period of time? Anyone? This time, it represents how long? It's not written here. It's the same like here, the same like here, the same like here, and the same like here, and the same like here, and the same like here. How long is this? This is one cycle of 100 hertz. This is one cycle of 100 hertz. This is 10,000 hertz. Yes, Harry, how much is 1 divided by 1,000 seconds? 1 millisecond, right? So this is all 1 millisecond depictions. So the Fourier representation is, so here you have frequency. So these two are the same, 1,000 hertz. It will be here, right? This is 10,000, will be here. So here you have 1,000, 10,000, 20,000, 100,000, etc. And the height is the amplitude. Is this distance here? Will be this distance here. So this height is this height. All right? Can you understand? It's simple, right? So it's useful when we want to represent complex waves. So these are pure tones. Oops. These are pure tones. This is the Fourier representation. These little fellows here are not the sound. This is the sound. Okay. Is it in different colors? It is, right? These are ticks of the graph only. So this pure tone is 200 hertz, 400 hertz. They all have the same height, meaning they have the same amplitude. If they are presented together, we have a complex waveform. And we can simply add for each point in time, we can add the height of each one of those waves, and we reach a complex waveform. These are harmonics. Most of them, most if not all of the sounds we hear in our day-to-day, they are complex sounds. They are just like light. What we see are a lot of different wavelengths at the same time, sounds the same. So when we represent by the Fourier spectrum, it's much more comfortable. So let me show you how different complex tones sound. So be prepared to adjust your volume. So first a pure tone that you already know, if it works. Why is it not working? All right, this sounds like 1,000 hertz. I don't remember, but it sounds like one. White noise. Okay, so this is Fourier representation, yes? So white noise is the addition of a lot of sounds covering almost, it looks like a straight line because it's a lot of all the little different frequencies and all with the same amplitude. If we would zoom in within here, more and more and more with a very high resolution, we would see small variations, okay? So white noise sounds like this. Like, oops, sorry. No, I don't have somehow the white noise. So white noise, you know, yes, this is white noise. And a violin. So different combinations. So in a violin, as you can see, you have a lot of different wavelengths, different sounds called harmonics that combine together. But we perceive as one sound, one unitary feeling, perception, one pitch. And this is the timbre of a given sound. This is the identity. That's how we discern perceptually between different instruments or different voices or different anything, because they are combinations of small different wavelengths. And the same, just like colors, the same perception can be achieved by different additions, different combinations of the wavelength components. This is the spectra of each of a piano, of a piano. Okay, as you saw, this is frequency, yes, and this is decibels. So as you saw, although we feel all these sounds as one unitary thing, most of them here we have some that they are almost a pure tone in the high notes. But look, those are a bunch of pure tones combined together, even though we feel as one sound, one pitch. Look at the low tones, how many. All right, so we finished 10 minutes before time. Questions? No, no questions. Okay. I'll take 5 minutes and then I'll start my office hours until 6. I'll be here. And next Monday, we will talk about our ears. Right?
Thank you.
You're welcome.
Thank you.
Thank you.
My pleasure.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
Bye, Michelle.
Bye.